Ever wondered how we could possibly mitigate the risks of lane veering due to driver negligence in manual driving? Well, the solution might be found in the realm of artificial intelligence, more specifically, in the application of convolutional neural networks, or as they're more commonly known, CNNs. In this project, a CNN was trained to correlate a vehicle-mounted camera image to a specific steering angle. This was then paired with a network client web application designed to communicate bidirectionally with a self-driving car simulation. This application allowed the system to receive data, predict a steering angle, and send a steering command all in real time. The result? Autonomous lane keeping on the data collection track and even successful navigation on roads the model had never experienced before. The objective was to implement a neural network to predict a steering angle based on an input image in a real-time simulation, and to establish communication between the simulation and the angle predicting model. It's a complex task that builds upon existing technology like computer vision for lane marking detection and HD maps, while also paving the way for a gradual transition to neural networks requiring extensive training sets. To achieve this, an algorithm was designed to download, balance, split, pre-process, train, and validate data to create the CNN model. A script was then used to receive simulation data and use the created model to predict the steering angle. This prediction was sent back to the vehicle as a steering command in real time. The process began with the manual recording of simulation image and steering data, which was saved to a Git repository and cloned to Google Colab. The data was then balanced to remove zero-angle driving bias by threshold, filtering discrete steering angle bins. The result was a well-trained model with a validation loss of just 0.02, indicating no overfitting and a high level of generalization. The model performed flawlessly on the trained track and demonstrated impressive performance on untrained tracks. Looking to the future, the potential applications of this technology are vast. For instance, it could be expanded to a hardware implementation using a mounted camera on an RC car. Images could then be sent to a CNN model loaded on a microcontroller interfaced with RC car components. After the model predicts the steering angle, it could send steering and throttle PWM commands to the steering servo and electronic speed control. In summary, this project has demonstrated the potential of convolutional neural networks in mitigating the risks of lane veering in manual driving. By training a model to relate an image to a steering angle and creating an application to communicate with a self-driving car simulation, autonomous lane keeping became a reality. This not only provides a solution to a pressing problem, but also paves the way for future advancements in the realm of self-driving technology.